Okay, having understood linear displacement, angular displacement, now let's focus towards acceleration. Alright, let's focus towards acceleration. Alright, now acceleration, now here it was distance covered s, now here I see that velocity v1 is at time t1, velocity v2 is at time t2. So what is acceleration? Obviously it would be v2 minus v1 over t2 minus t1, or rather in differentiation that's what we have learned, dv over dt is acceleration. Alright, okay, so similarly over here, now that dv which is there is v2 minus v1 and difference in time is t2 minus t1 is equal to acceleration. Alright, now acceleration, so it's acceleration, if we want to depict, we can depict it as v over t, v over t, v already we saw is meters per second over time, so time goes down, so it becomes s upon t square, so it is meter per second square. That's the unit for acceleration. Okay, now let's move on to rotational movement. Now in case of rotational movement, what happens is, now I say that, okay, let me do it this way. As I told, we are moving in anti-clockwise direction. The angular velocity here is omega 1 at time t1, and angular velocity over here is omega 2 at time t2. So what is angular acceleration? Angular acceleration is represented by alpha. So obviously as we did in linear, see, it becomes so very analogic. Alright, you know linear, you can set it up for rotational. So omega 2 minus omega 1 divided by t2 minus t1 becomes alpha. Alright, again as I did v over t, it is omega over t, so that is theta t over t, that is theta over t square. Theta we told, we saw it earlier that theta we saw earlier could be in degrees or could be in radians. This was the conversion factor that we saw. So it would be, this t would come down, so it would form theta upon t square, so it would be radian per second square. That's how the acceleration, the linear acceleration and angular acceleration goes. Linear acceleration is referred by a, angular acceleration is referred by alpha. Now let us get into relationship between linear and angular. S is equal to r theta, where r is radius vector. Alright, radius vector is always pointing from inside to out. Alright, from inside to out is the radius vector. I mentioned it over here. Alright, S is equal to r theta, V is equal to r omega, and A is equal to r alpha. These are all rotational and these are all linear. Alright, easy to keep in mind. Just to multiply whatever is the, we know S is theta, V is omega, A is alpha, just multiply it with r, so that becomes the conversion factor from linear to rotational motion. Alright, now about kinematic equations. I'm sure you are all aware about kinematic equations in linear format. So this was what you had learned, V is equal to u plus at. This V is equal to u plus at is also very simple. See, it can go from here, like see, this, see, it is v2 is final velocity. Normally initial velocity we write it as u upon t is acceleration, so just take t there and u there. Alright, so t there, so it would be v minus u is equal to at, and then take u there, it becomes u plus at. So anytime 7 if you forget, that's all okay, you can just go back to your definition for acceleration and derive it. Okay, anyways, so v is equal to u plus at, s is equal to ut plus half at square. If you remember, we have derived this in our 11th standard in vectors, all right, in triangle. Okay, s is equal to ut plus half at square, v square is equal to u square plus 2as. These were the kinematic equations that we had learned in 11th and lower classes. Okay, now we are going to move into rotational motion. All right, so when we come to rotational motion, your u turns to omega 0, your v turns to omega initial. Now here we had written omega 1, instead of that I can write it as omega, and here I can omega 0, sorry, original omega o, and this can be omega. All right, final angular velocity could be omega. So v omega, u omega 0, a alpha t, s theta, u omega 0, t remains t, half a alpha t square, v square, final velocity, final linear velocity, final angular velocity, initial angular velocity, initial linear velocity, 2 remains 2, doesn't change in rotational motion, the number remains the same. All right, so a alpha s theta. So that's what you have got to keep in mind now along with this rotation. So this is all rotational, fine. Okay, I hope this is all clear. Now along with this, let's try and understand a bit of circular motion in depth. All right,